My favorite stuff to do.
Oh my god, really? Okay. So before we get started here on rational expressions, I want to know, what does the word rational mean? Rational, fractional. Well, you must have had me last year. Yeah. Rational, fractional. Fractional. Okay. Rational, fractional. I like that because it rhymes, first of all. But we have rational expressions really just are in fraction form. Okay, expressions that are in fraction form. And in fact, the root of the word rational is ratio, which is comparing two items, or really a division problem for fraction. And in fact, when you even look at this word fraction, it has ratio right in it. R-A-T-I-O. Look at that. Fraction, ratio, same thing. Okay, so today we're looking at fractional expressions. And there's a few things that we want to really talk about today, which you may have learned in Algebra 2. I hope you learned domain of a few things in Algebra 2. Domain is something we spend a lot of time talking about in this class, and it's certainly something that we really want to understand. If you have your graphing calculators, you might want to get those out, because your calculators can really help you figure out domain as well. And so you can use your calculator as a hey, here's a good idea of domain. So there's really three things that I want to, before we start, just go over really fast about domain. So you should write these things down. It's for extra information here. Right now, starting today, there's three things we want to be aware of when we talk about domain. And we'll add to this as we learn more and more. So when I talk about domain, graphically speaking, domain is how far left and right the graph goes. And so if you have a graph to look at, then you can use that graph to help you figure out domain. And so for a few examples, here I have 3 examples. So first of all, for any polynomial, and any polynomial might be like 2x cubed minus 3x squared plus 7, something like that, okay? This is a regular polynomial. And if I were to take that polynomial, I'll just leave that, it doesn't really matter. If I were to graph that polynomial, so I'm in my y equals menu, and if I were to just graph it, 2x cubed minus 3, I have no idea what this is really going to look like necessarily, so it might not be like much, but all right. Oh, that's interesting. Let's try that. Okay. Looks something like that. Yeah. And so that is a nice smooth curve. Would you say it's a nice smooth curve? Ignoring the pixels. Okay, right? This is not a retina display screen, so, you have to imagine it. But it is a nice smooth curve. But any polynomial is always going to be nice and smooth, and it goes on forever. Okay. And when we look at those polynomials, what we want to imagine is, like, the polynomial doesn't stop right here, does it? It continues up forever, continues down forever. But really what's happening, like especially with a quadratic here, parabola, these arrows are pointing up, but are they only going vertical? No, they move out as well, right? They grow to the left and they grow to the right. So that's what I'm talking about when I say how far left and right does the graph go. They move forever to the left and forever to the right. All the x values that are negative and all the x values that are positive. So we say that the domain is all of those real numbers. And so all real numbers is the domain of any polynomial function. Okay. because it goes forever to the left and forever to the right. Now, with that knowledge, when we compare it to other graphs, like a square root, anytime we have an even root, we have a different situation happening. So I want to show, let's see, the square root of x minus x plus 4. Let's do x plus 4. Does anyone know what a square root function looks like? Square root. Does anyone know? Is that a swoop? Okay, I call it the swoop. All right, so here's what it looks like if you didn't know that. Swoop. Makes it fun to say. All right, so there it is. So I'm going to type in the square root of x plus 4. Now, even roots, and this is specific to even roots. Odd roots, like a cube root or a fifth root, work all the time, but even roots are very special in that they don't work all the time. I cannot plug in every value for x. So if I were to graph that, it says swoop. It's shifted to the left 4. So my question to you is, does that graph go forever to the left and forever to the right? No, it doesn't. It stops here at -4, doesn't it? And then so when we look at this, the domain is basically, where do you see the graph? Well, I see the graph on the x-axis. I see a graph for all the x values that are larger than and equal to -4. So the domain of this function is x is greater than or equal to -4. And that's the domain. And so if you have a picture, it can really help you figure out the domain. Now, the other thing you want to pay attention to are fractions, rational expressions, F-R-A-C-T. I can't talk and write today. So, for instance, something like 3 over x plus 2. Sure. This graph is very interesting, and when I look at this graph, 3 over the whole x plus 2, so you'll see I put that whole denominator in parentheses. And if I were to graph this, something very weird is happening in the middle. What's happening in the middle of that graph? It splits. Yeah, we say that diverges. So you see the left side of that area goes down, and then on the right side it's going upwards. So we say they diverge. Okay, but you'll notice it's very different than these polynomials. It's not a smooth, continuous curve. This is two separate pieces, shall we say. When this happens, right here, it's happening at -2. And where do you think that comes from in this function? The denominator, yeah, denominators cannot equal 0. And what happens is when x is not allowed to be -2, every other number works. But here, what happens, if I plug in -2, -2 plus 2 is 0. We get a 0 in the denominator. What happens when a 0 is under? It's undefined. Very good. When the 0 is under, it's undefined. I think I've said that before in this class, right? Undefined. When the 0 is under, it's undefined. And when we think about slopes, what does an undefined slope look like? Isn't that a vertical line? Yeah. So we create these asymptotes, and that's what happens graphically. Whenever we have a variable in the denominator, we're going to get those crazy things. So there's here even roots and denominators that we need to look out for today. So I'll show you how to do that a little more specifically here. So example 1, find the domain of the expression. Another way to say that is what x values don't work. Find the domain of the expression. And again, you can always use a graphing calculator to help you out if you were ever stuck. Find the domain of the expression. So if you wanted to, you could put letter A as a function and y equals if you wanted to, but I bet you know the shape of this. What's it look like? It's a parabola. Yeah, how do you know it's a parabola?
Because it's the high stars.
Very good. The highest power of the degree is 2. It's x squared, and all x squareds are parabolas. It's also not parabola. And so how far left and how far right does this graph go?
Infinite.
Infinitely to the left and infinitely to the right. And on the x-axis, that'd be negative x values all the way to positive x values. It's all real numbers. So you could write all real numbers. What that means is I can think of any x value and I can plug it in and it'll give me an output, no problem. I can plug in negative values for x, I can plug in positive values for x, I can plug in fractions, and I'm always going to get an input-output pair. If you want to abbreviate, you can use bold-faced R. That is the notation when in higher math for the real numbers. And you can just put R for all numbers. Means the same thing. Okay. Letter B here, what do we have? A fraction. And anytime we have a fraction, I know that my denominator is not allowed to equal 0. And that's really, really, really important. What I'm going to do first, before I try and figure that out, is factor, factor, factor. Factor first is like another alliteration I love. I love alliteration. It's great. Okay, so the numerator factors, doesn't it? How does that factor? Good, x minus 1, x plus 1. And our denominator factors, x times x is x squared. What times what is positive 6? Negative 6 and negative 1. Also, negative 2 and negative 3. And we're going to choose negative 1 and negative 6, right? Okay, good. All right, so factored form is really, really important in almost everything we do when we want to graph. So we love factored form. And what do you notice here about those factors? Yeah, something happens here. I'm actually not going to cancel it right now because they didn't ask me to. But what happens when you can, does anyone remember what happens when you have factors that reduce top and bottom? What graphical thing happens? It's a hole in the graph, yeah. A spot in the graph that doesn't work. It's kind of interesting. But right here in factored form, we're going to look just at those denominator bubbles. And we're going to say that those denominator bubbles can't equal 0. Each bubble is not allowed to be 0, which means if I move the 1 over, x is not allowed to equal positive 1, and x is not allowed to equal positive 6. These are 2 excluded values. And so I would just say this is the domain. X cannot equal 1 and x cannot equal 6. Everything else works just fine. All right. Letter C is an even root. And even roots we have to pay close attention to because of this problem. What's the square root of negative 25? And I stands for imaginary. Yeah. And imaginary, meaning it's not really there, which is why on the graph of this square root swoop, we only see half a picture because the other side of it is imaginary. It's not really there. Does that make sense to you? Okay. And so anytime we have an even root, getting imaginary values can happen, which is why we only see a portion of the picture. So anytime you have an even root, you're going to take that root, that even root, and say, hey, you must be greater than or equal to 0. Why must that root be greater than or equal to 0? It can't be negative. Yeah, you have to be positive in order for you to work properly. Does that make sense to you? Okay, and you can also be 0. 0 is fine. You can take the square root of 0. It's fine. But you can't be negative, and so that's what we tell it. And so once again, this is a little equation we can solve. How do I get rid of that square root? Square both sides. The square and the square root cancel out, leaving me the guts of the equation. The innards, the guts. Yeah. I have lots of fun, really mathematical words, like guts. Okay. And then how do we solve for x? Add 7. So we get 3x greater than or equal to 7, and then divide by 3. So we'd get 7x is greater than or equal to 7/3. And ladies and gentlemen, that is the domain, which is kind of nice. So anytime you have a root, you can just solve the equation, and that is the domain. I want to remind you, what if that equation was negative 3x is greater than or equal to 7? You would divide by negative 3 and remember to flip the inequality symbol. Anytime you multiply or divide by a negative, you need to flip that inequality symbol, okay? All right, so 3 things to look out for on domain, fractions and roots being the main 2. Usually it's all real numbers. All right, any questions on those? Sample 2. Write the rational expression in simplest form. Bless you. To write these expressions in simplest form, we want to factor first. Factor is what we're doing. And we kind of, we actually, I used to teach this in Algebra 1, so we would learn how to factor. We learn how to double bubble, and then right away we come to rational expressions where all we're doing is factoring more. So we want to factor, and then maybe we can pop some bubbles if they work. All right, so I have 3xy over xy plus x. And what we remember is I just went over a whole bunch of ways for you to factor in the last week. So not only is there regular double bubble, but we have GCF, greatest common factor. If there's 4 terms, we've got factor by grouping. We've got sum and difference of cubes, difference of squares, perfect square trinomials. There's all kinds of different ways to factor. So you might need to review your notes to recall some of those things. On letter A, what can we do to factor? GCF. There is a greatest common factor in that denominator. Can I just cross off the xy's on top of mine?
No.
No. It's not in factored form. If you need me to prove that to you, we can use some numbers. All right. So in the denominator here, I'm going to go ahead. This is 3 times x times y on the top. And what's the GCF in the denominator?
X.
X. And if I take out the x, what's left behind? Y plus 1. Very good. Taking out the GCF can be hard for some. I just want to make sure that if you have trouble with it, all you need to do is redistribute to make sure you did it right. So x times y is xy, and x times 1 is x, so we know we did it correctly. Now that everything is connected by multiplication, now we can cross stuff off. But before I do that, I'm going to add in here what things don't work. X is not allowed to be 0. Why? Yeah, if I plug in a 0 in place of that x, 0 times anything, I'd have a 0 in the denominator, which means we'd be dividing by 0, which is not allowed. What else? Y cannot equal -1. Very good. These are the excluded values. I think that it's really nice to just start thinking about those. They are the things that make that denominator 0, and we want to make sure that we're always aware we cannot have those as answers, essentially. Can't be part of our solution. So now that we've got this factored, what reduces? The x's. X on top, x divided by x is 1. So we're left with 3 times y in the numerator and y plus 1 in the denominator. And we've got some exclusions that we want to also include in our answer. Now, I will have this little thing. Your book might not have this part. That y cannot equal -1, okay? And the reason your book might not have that is because your book looks at this answer and says, oh, it's understood that y is not allowed to be -1. I don't know if you understand that yet or not. I certainly don't. So I'm just spelling it out. Does that make sense to you? We're being very explicit instead of being just sort of implied, okay? So I'm more about just being upfront with things. All right, ladies and gentlemen, letter B, what can we do? Factor out. Okay, so there's a GCF first. Greatest common factor first. If I take out the x, what's left behind? Good, x squared minus 5x plus 6. And then, now that I've taken that out, I can go ahead and double bubble everything else. How does x squared minus 5x plus 6 factor? X minus 3 and x minus 2, very good. It's my favorite trinomial because it's the most widely missed. Like wouldn't negative 6 and positive 1 work?
No.
Very good. So people that if you're not paying attention, they might think that this works, but it doesn't, because -6 times +1 would give you a -6, not that +6 we need. Okay, so careful. How does x squared minus 4 factor? Yeah, x plus 2 and x minus 2. And so right here, now that we're fully factored, I want to look at those exclusions. So what is x not allowed to be? Plus or minus 2. Right there, if I plug in a -2, it's not going to work. And if I plug in a +2, I'm going to get undefined. Do I care about the x on top? No, it's really just the denominator that we care about. And what reduces? Yeah. Cool. So here we go. X minus 3. Now, my question to you then, the very last thing here, do I need to redistribute my x? No. No, we actually prefer to have things in factored form, so it's really absolutely unnecessary to redistribute because we can see so much more if it's factored. Graphically speaking, that is. Okay? Do you guys have any questions for me? All right. You maybe